Hi and welcome back. So let's continue our work on valence electrons. We're going to be doing ion examples today. We're going to be adding or removing electrons from neutral elements and seeing how that changes how we write out the orbital diagrams and the electron configurations. And then we'll be tracking the core and valence electrons again. So got three different scenarios to compare and contrast, but here's the basic summary if you wanted to boil down this video into one sentence, which is when it comes to ions, you'll be adding or removing electrons from the valence shell. That highest n value principal quantum number, aka the outermost electrons, that's where you're going to be adding or removing electrons. So three scenarios today. We'll be spending probably most of our time here. We're going to be comparing an anion versus a neutral element versus a cation. So here we have two ions, and we're going to be comparing it to a neon, and they're all going to have the same number of electrons. So you may be thinking, maybe they're all going to have the same electron configurations and orbital diagrams. Mostly right, okay? We'll have to talk because I said that word mostly, all right? But I like the way you're thinking. All right, scenario two, we're going to compare an element that's neutral, lose some electrons, lose even more electrons. How does that affect its electron configuration and orbital diagram? All right, and then lastly, kind of just for fun, a quick example, comparing neutral hydrogen to removing an electron from it, or the other direction, adding an electron to hydrogen. Yeah, this one's not as common, but you can do that too. Let's start with scenario one. So we're going to be comparing the fluoride anion, F minus, to neon, to the sodium cation, all right? And to make the sodium cation and the fluoride anion, I'm going to do a reaction with them on paper. Not exactly safe to demonstrate in my office here, but maybe you can use your imagination, all right? But I wrote these little side notes, all right? Like sodium metal. If you were to get sodium metal, I mean, you don't find sodium metal in nature because it's already reacted to become sodium cation. If you create sodium metal in the lab, it's deadly, all right? You drop some in water, you can have an explosion, all right? And so this is a very reactive element. Having that one valence electron can make it very reactive, all right? Versus sodium cation, this is essential for life, all right? Like in sodium chloride, table salt, you have sodium cation and chloride anion, right? One electron makes a world of difference. Similar thing can be said for fluorine, all right? We're not talking about fluorine gas, all right? That's deadly too. Having 7 valence electrons, deadly, all right? Things are less reactive when you either have 8 valence electrons or 0 valence electrons, generally speaking. We're going to add an electron to the fluorine. Actually, we'll just take it from the sodium. We'll add it to the fluorine. It's going to have a minus charge. And so you have a deadly gas versus fluoride, which can be used to prevent tooth decay. So two very different stories by virtue of one electron change. Neon, it doesn't get a side note. Neon is a noble gas, unreactive, but there you go. All right, so let's do this reaction, all right? And I know we haven't really talked about reactions yet, but basically, I think we can do this. We're going to move one electron from neutral sodium, and we're going to put it onto the fluorine, okay? And that's going to create a plus charge and a minus charge, all right? Now you may be thinking, oh, if you're adding something, shouldn't that be like plus means adding? Here's a plus sign. There we go. But we're adding something that has a negative number. So we have more of the negatives than the positives, which is why we're ending up with a minus on the F. Whereas sodium is losing something that has a negative number. So it ends up having more protons, the positive things, compared to the electrons. All right. So here I just pre-did the work of analyzing sodium and fluorine, or at least most of the work. All right, here's sodium and here's fluorine. 11 protons, 11 electrons, 9 protons, 9 electrons. Okay, on the periodic table, we are kind of living here today. Fluorine is number 9, neon is number 10, sodium is 11. All right, so we're working with these neighbors. All right, so let's do the reaction. Well, first, let's write them out in their neutral states. All right, sodium, as written on the periodic table, 11 protons, 11 electrons. So let's fill that in. 1, 2, 4, 10, and then there is 11. Okay, and then let's do fluorine. All right, we're gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, I don't know if you felt this, but maybe you felt the urge to just put one more electron and just fill it and pair it. Okay. That's kind of the urge between these two elements, all right? Fluorine has space for one more electron, and sodium has an extra electron that it can get rid of, all right? So one thing you're gonna see and hear about and study numerous times is metals are reactive, non-metals are reactive, and the way they react is that your metals will give their electrons to the non-metals if they're put together. And that's what happens here. All right. So again, this is not like the main focus of this video isn't to learn reactions, but it's to learn the electrons. But we're just using this reaction just to show something. So this electron right here will go there. All right. And I'll keep that same color of blue there. All right. If you're wondering, oh, I flipped the spin, is that okay? Yeah, that is okay. Go ahead and flip that spin. All right. And now we're going to make a new picture for sodium and for fluorine. So now this electron will be gone. And now we've gone from 11 to 10 electrons. Okay. And if you're keeping track of valence electrons, sodium had 1 valence electron, and then it lost it. So now it has 0. Okay. See, this was our valence shell, okay, out here. And now it's gone. We just flicked it away. All right, fluorine had 7 valence electrons. 1, 2, 4, 6, 7. And then we added another one. So now we're at 8 valence electrons. Okay. But in terms of total electron count, we added that 1, and now it's at 10. All right, same number of electrons in the world. You can't create or destroy matter unless you're in a nuclear reactor, but otherwise you can't. We had 11 plus 9 before. That's 20 electrons in this little universe, and now it's 10 plus 10. It's still 20 electrons. So in chemistry, you don't create or destroy electrons. Chemistry is just a movement of electrons. All right, so let's put this into a more formal framework. All right, pause and copy this if you need to. But basically what I did here was I analyzed the fluoride anion. All right, we added that 10th electron. So now we went from 2p5 to 2p6. And then the sodium cation, we had a 3s1 originally, but then we got rid of it. All right, so again, pause if you need to. I'll just count to 5 here. Okay, so hopefully you had a chance to do this. All right, we haven't done the orbital diagrams there. I'll get there in a minute. Okay, but again, I'll say this one more time. Sodium used to be 3s1, but we got rid of it. Okay, so you can scratch that out. Or I've seen some students do this. They'll write a 0 there to remind themselves they used to have an electron there, but now they don't. All right. I wouldn't necessarily type this into like a homework program or something, but For me in my classes, like if I had a free response section and someone wrote that, I would give that full credit. I see good awareness there. But maybe not on a homework software package. If it was a homework software package, I would probably just leave it like that. All right. But yeah, the 3s electron is gone. Okay. And so what will that do to our valence electron count? I'll show that in a minute. Okay. Let's first fill out these orbital diagrams. All right, so 1s2, 2s2, 2p5 became 2p6. So we're going to add 10 electrons to this diagram. 1, 2, tell you what, we were in red before, so I'll just stick with that. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'll use blue to signify the electron that sodium gave to that fluoride. Okay. And it didn't have to be a sodium. It could have been any other element that gives away electrons. But in our story, this sodium gave it to the fluoride. Fluorine to become a fluoride. All right? And so there we go. If we're counting valence electrons and core electrons and all that stuff, previous noble gas was helium. So that is going to be 2 core electrons. And then here, everything here is 8 valence electrons. Okay, we went from 7 in neutral fluorine to 8. Okay, neon, well, we didn't mess with anything, so it should just be everything as normal. 1, 2, 3, 4, 10. All right. And so neon, like we said in a different video, if you didn't see it, I'll just summarize it. For noble gas, you can't write itself as its electron configuration when you're abbreviating it. You have to use the previous noble gas. Okay, and so hopefully you can see here, even though neon's a noble gas, we used a previous one of neon. So we have 2 core electrons. Or not of neon, of helium. Okay, so we have 2 core electrons, and we have 8 valence electrons once again. So I said compare and contrast. You're like, everything's looking the same so far. It's probably that last one where it's going to be different. Yeah, you're right. Okay, but here's what we've done so far. All right, we've gotten kind of everything to a noble gas configuration. That's going to be a constant theme in chemistry where you can explain reactions and the stability, the existence of many compounds by elements in the compounds having the same number of electrons as a noble gas. Right? This seems to explain a lot of phenomenon. Even without using like a ton of advanced math, you can make a lot of compound predictions. All right. So like fluoride got to 10, sodium got to 10. Neon's already a noble gas. You can do this for so many elements. Like you leave out iron, it gets rusty. You're going to have iron oxides. That's going to have oxygen with 2 electrons on it. It's going to become a 10 as well. I mean, we can do this for so many elements. All right. So yeah, for sodium, we used to have, I'll go like this. We used to have a 3s electron. It used to be there. I guess I should have filled out everything else first. Okay, fine. 1, 2. We'll just pretend I didn't do that yet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's what sodium used to be. So if we were asked what's the orbital diagram electron configuration for sodium, we would have left at 3s1. Like we did on the previous page. This right here, all this would be our core electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 core electrons, which would be right here. And this could be rewritten in a condensed electron configuration as neon 3s1. But again, we gave away that electron to fluorine, so now it's gone. Okay, and this is gone. Okay. So, what happened? Okay, what are we left with? So I want you to notice this. The electron configurations for these three different species are exactly the same. 1s2, 2s2, 2p6. The orbital diagrams are exactly the same as well. All right, but look at this condensed electron configuration. It's the same for fluoride and neon, but it's different for sodium. Okay? Said another way, sodium has 0 valence electrons. Okay? And if you're going to write a condensed electron configuration, the answer would be just plain old neon. This happens only when you have a cation. Okay? You'll notice, again, for noble gas, it's not like we wrote just helium. All right? We have those 8 valence electrons. Having 8 valence electrons is one way of defining what it means to be a noble gas, except for helium, which is 2, but 8 valence electrons otherwise. But for metal cations, you lose some or all of your valence electrons, and then it's possible to get to a 0 valence electron count. So you wouldn't say 8. No, sodium used to have 1 and it lost it, so it's a 0. Right? So to keep track of score, F minus versus neon versus sodium. Okay, same electron configuration, same orbital diagram, but we're going to have different condensed electron configuration and different number of valence electrons. Okay, what's considered core and valence electrons will be different for the cation. Oops, forgot that plus sign. Will be different for the cation compared to these two. All right, so that's kind of a common pitfall. So hopefully I addressed that well there. All right, let's keep moving. All right, so now we're going to be comparing tin in its elemental neutral state versus a 2+ cation state versus a 4+ cation. And comparing these situations, we lost 2 electrons here. Lose 2 electrons. And then we're going to lose another 2 electrons here. All right. And it has to deal with the valence electrons again. All right. The electrons that are furthest away from the atom, okay, the electron shell, that valence shell, that is the most accessible for chemistry. That's where you can add stuff. It's the most readily accessible. That's also where you can remove stuff. So that means when we go to our orbital diagrams and our electron configurations, that's where we're going to be doing our adding and subtracting, just like we saw with the sodium and fluorine examples. All right, so go ahead and do the electron configurations, full and condensed for tin. Let's just start with neutral tin as well as the orbital diagram. All right. If you already know how to do it, you just want to copy, I guess here it is. But I encourage you, even if you know how to do it, just do it. Okay. All right. I'll assume that was enough time for you to pause and get that figured out. All right, so now let's do the problem, okay? I think the easiest way, the simplest and fastest way to explain this is to just work off of this same electron configurations and diagram. All right, so I want you to first take a guess going from neutral to 2+, which 2 electrons are going to be removed. All right, and we'll just cross them out. All right, so it's going to be the outermost. So on the orbital diagram, we would just lose these two. All right. So you could cross them off, or if you were asked to write the orbital diagram of tin 2+, you would just write everything up to here, but with nothing here. All right. So those are gone. How about going to a 4+? Which 2 electrons are you going to lose? Okay. So think on that. Okay, so let me reveal the answer. So it's going to be the 5s electrons. So I guess I should finish the 2+. So in the 2+ example, we lost these two. All right. And then if we were going to lose another 2 electrons, it would be those. All right. So in an orbital diagram, maybe visually, it felt like more tempting to take away from the 4D. So maybe it would have helped if you had circled what your valence was. Okay. But remember that even though 4D is written here, in reality, 4D, by having a 4 means that in reality, it's actually like right there in reality. We don't write the orbital diagram that way all the time because we like to write in the order of how it fills. But in real life, okay, 4D is actually there. Okay, to just keep things simple, you can just write things this way, but just remove your valence electrons. Right, so I got rid of the 5s. Okay, so to like fully answer the question of the valence electrons between these 3 species, okay, Sn, like if we were writing an electron configuration, it would just simply, it would be 5s2 krypton, 5s2 4010 5p2. All right, if we were doing a tin 2+, those went away. And then for 4+, those went away. So we have that. Okay. So tin had, well, it's 50, so we had 46 core electrons, 4 valence electrons, and we're most interested in that valence count. Oh, now I'm on the screen. And then for tin 2+, core doesn't change. It's the core. All right, 46 core electrons, 2 valence electrons. And then for tin 4+, 46 core electrons, but we've lost all of our valence, so we have 0 valence electrons. All right, so hopefully that helped, and yeah, just kind of a closing note, putting you in a teacher's perspective. Like the reason why you're like, why do you choose tin? It's like kind of a big element, you know. Well, first, in class, I think any one-on-one course, you'll reasonably be considered to do these sorts of elements like tin or lead, bismuth, whatever. So I think that's reasonable. But I chose tin because I thought actually it'd be interesting. At some point in some Chem 101 intro chem curriculums, you'll be learning about the different charges on different metals. And main group metals like the S block and the P block are part of it, but you might be learning some different charges here. All right, and then one of the things you might learn about is that some metals can lose different number of electrons. All right, one of my favorite examples is iron. It can lose 2 electrons to become a 2+, or it can lose 3 electrons. It can lose a third electron to lose a total of 3 electrons. It can be 3+. And like you drive around and you look at different geology and different compounds like rocks that are like darker, they can have like iron 2 plus, and like rocks, minerals that are more on the orangish reddish side, reminds you of rust. Those are going to have like 3 plus, iron 3 plus. So like that different charge state is important. And tin's one of those examples as well. Tin as well as lead can be 2 plus, or it can be 4 plus. So you lose one, you lose boom boom those 2 valence electrons, 2 plus. You lose the next 2, you become 4 plus. All right, and yeah, that can be a story for some of the other elements as well. All right, last example is hydrogen, scenario 3. So hydrogen is normally found on the periodic table, 1 proton and 1 electron. Here it is, and it would have an electron configuration of 1s1, with that being the orbital diagram. Remove an electron, your electron configuration becomes 1s0, and you have nothing. You have no electrons at all. Whereas here, if we were to go the other direction, add an electron, you would have this so-called hydride ion. Not common, but it can happen. This is more common for ions of hydrogen, the proton. But for the hydride, you add an electron, you go 1s2, and you would have 2 electrons like that. All right, so that was pretty much it there, and so that'll be the close of my video. So hopefully this helps, and let me know if you have any questions. Thanks, and take care.